In this video, we're going to talk about chemical equations. We'll talk about the overall formatting that we use to describe a chemical reaction, and we'll also talk about how to balance chemical equations as well. So let's start with formatting. So to write a chemical equation, we'll be writing out kind of a before and after picture. Here are the chemicals that we start with, our reactants, and we expect them to produce products. And so this before and after, in a sense, is going to be our reactants that then transform into our products. And to indicate the difference between these two, we use an arrow. It's kind of like an action, like these become these new things. And the arrow is important. It's not an equal sign because even though our reactants will become our products, they're not the same thing. And so the arrow is the appropriate way to do it. For any chemical reaction, we are going to try to represent a lot of information with very little actually written. And so it's an exercise in taking a lot and consolidating it. And we'll do this again and again in chemistry. Chemists love to represent lots of information with just a few symbols. It's one of our favorite things, I think. So we'll have reactants that will have chemical formulas rather than names. And so here, the chemical formulas that I'm using as variables are A, B, C, and D. And now these might be interpreted later on as something like what we have in our example. Methane would be one chemical formula. Oxygen, carbon dioxide, and water would be another chemical formula. That would all kind of be in there. Then we would have in front of it a mole ratio that tells us how much of that compound reacts with how much of another compound to produce how much of another one. And this is going to be a simple whole number ratio that is indicated by the number in front of the chemical formula. So here it's the lowercase a, b, c, and d if we're thinking about this in a generic variable format. In our example, that mole ratio is represented by this 2 in front of the oxygen and the 2 in front of the water. Now, there is still information being communicated about the mole ratio of the carbon dioxide and the methane. It's actually, if there's nothing there, it's a 1. Because if we're writing out the chemical formula, it implies that there's at least 1 mole of this reactant to react with 2 moles of oxygen. So whenever we have this blank space here, that really means 1. So besides our arrow, our mole ratios, and our chemical formulas, the other important part of a chemical equation is the state the chemical is in during the reaction. And that's going to be listed after the chemical formula every time. And so you'll do this for each chemical because they could be in different states. They're not all necessarily going to be in the same one. And so for our example reaction, our methane is going to be a gas. So we put a G in parentheses. So will our oxygen, and it produces carbon dioxide and water gas as well. So our different physical states that we can use in our chemical equations are listed right here. There's S for solid, G for gas, L for liquid, and AQ, which is aqueous, which is not necessarily a physical state like we think of states of matter. Instead, it implies that whatever chemical we're talking about is it dissolved in water as a solute, and that water is its solvent. So it's a way of saying we've got tons of water around this chemical when this reaction is taking place without writing water as part of the reaction. And that kind of brings me to an important point about writing out chemical reactions. We're only going to write the chemicals that are participating in the reaction. So that means we won't write out things that are just the solvent in a reaction that aren't participating. So I wouldn't write water in my chemical reaction unless I actually consumed a water molecule to make a product or formed a water molecule as a product. And what these chemical reactions are really doing, in my opinion, is telling a story. And so every single chemical equation that you look at or you write yourself is actually a lot of information. And so here is a story version of a chemical equation. And I'm going to highlight the pieces of it that we would, or the information we would need to put it into a chemical formula or chemical equation. So we'll take this big paragraph and condense it down to one line and have all the same information. So it says that concentrated HCl, hydrochloric acid, is a liquid and is diluted in 1 liter of water in a beaker. Now, in a separate beaker, sodium hydroxide, NaOH, pellets are dissolved in 1 liter of water as well. Now, the sodium hydroxide solution is then added to the hydrochloric acid solution. And after a while, it'll get hot. It might even bubble. The pH is tested, and we see that there's a neutral pH, that there's neither an acid or a base, and that's confirmed. Therefore, we've got sodium chloride dissolved in water as the only product that is present in the beaker. All right. So there were a lot of words there I didn't actually highlight. So if I was going to write this out, I can say right away that I know that HCl is one of my reactants, and my other reactant that it's combined with before we form the products is sodium hydroxide. And so these are my reactants. I'll then draw an arrow to show that these reactants will undergo a chemical reaction. They'll form the product. And the product that we have is sodium chloride dissolved in water. So I'm going to put the sodium chloride here for now. Now, water is listed as something my reactants are dissolved in and also what my product is dissolved in. So do I include the water on the reactant side and the product side? It's a good question. Well, in my reactants, I'm not going to use the water to form my product. My product is going to be this sodium and this chloride and maybe something else. That's coming from this chloride here and the sodium here in my reactants. But then I have some other elements that aren't accounted for in my products right now. Within my reactants, I also have a hydrogen and an OH. And these are actually going to combine when we talk a little bit later about types of chemical reactions. And this is an acid-base reaction. Those will create a water molecule. So that hydrochloric acid and that sodium hydroxide just themselves react, and they produce a sodium chloride compound and water molecule. So I don't actually need to include water in my reactants because it's not actually participating in the reaction. So I'm going to go ahead and say that my hydrochloric acid is aqueous, and that's going to let everyone know the piece of information that this concentrated hydrochloric acid is diluted in water. So there is lots of water present, and we're not leaving that information out. We're just calling it aqueous instead of writing it out into the chemical reaction because that water isn't actually doing anything. Now my sodium chloride is dissolved in water too in my product, so that means its phase is also aqueous. And my water is created and it's surrounded by more water, but if it's the solvent and it can't be the solute. So water dissolved in water is just more water. And so it can't ever have the designation aqueous because that means to be dissolved in water. So in this case with the water, I'll make the designation for the physical state liquid. All right. So now we have all of our reactants and our products written out. We have our states. And now we need to balance this equation. So I have on my reactant side, I have 2 hydrogen, I have a chlorine, and I have a sodium, and I have an oxygen. And on my product side, I have 1 sodium, I have 1 chlorine, 1 oxygen, and 2 hydrogen. So this is a balanced reaction. And we're going to talk about the steps to balancing a reaction here next. So I'll be able to just write this as is, and that will be my interpretation of this story of how this chemical reaction happened. So let's look at how to balance these equations and what that really means. So when we have just the reactants and products that we know will occur, like if we combine these 2 reactants, we'll form these products. We need to make sure that we are observing the conservation of mass, the law of conservation of mass, which is that we're not going to create mass out of nowhere, and we're not going to destroy mass into nothingness. And so whatever we start with, we have to finish with. And that means that we're going to need to make sure we have the same number of atoms of each element that we have in our reactants, and we'll have that same number of atoms of those elements in our products. And we do this by balancing the reaction with our mole ratio, the coefficient that comes before the chemical formula in our chemical reaction equation. So here's our example of butane and oxygen undergoing combustion and forming carbon dioxide and water. And we can see right away that I have 4 carbon atoms in my reactants and only 1 in my product. I've got 10 hydrogen atoms in my reactants and only 2 in my products. So we aren't representing a conservation of mass. But if we make sure we have the same number of atoms on both sides of the arrow for each element, then we will be conserving mass. We'll have the same number of things on both before and after the reaction takes place. And so we do that by making sure the number of atoms is the same. So if I put a 2 in front of my butane and a 13 in front of my oxygen, an 8 in front of my carbon, and a 10 in front of my water, I'm going to have the same number of carbon atoms on both sides of the arrow, and the same number of hydrogens and the same number of oxygens. And I could count that up real quick. So I have 8 carbon on my reactants, and I have 8 carbon on my products. And what I'm doing to determine that number of carbon atoms is I'm taking my coefficient and I'm multiplying it by the subscript that follows the element. And that tells me the number of carbons I have. So that's 2 times 4 carbon will give me 8 carbon total on my reactant side. Similarly, here on the product side, I have 8 as my coefficient, and I have nothing as my subscript. So that's going to be 8 times 1 will give me 8 carbon atoms on my product side. And I can do that for hydrogen. I see I have 20 on both sides. And for my oxygen, I have 26 on both sides of my equation if I'm multiplying that coefficient by the subscript. So, so I can interpret this in a couple ways. One, I can read this as 2 molecules of butane reacts with 13 molecules of oxygen to form 8 molecules of carbon dioxide and 10 molecules of water, and that's correct. I probably won't be working on that small of a scale in the lab. Instead, I'll probably have a lot of butane, a lot of oxygen, developing or forming a lot of carbon dioxide and a lot of water. So we can interpret those numbers in front as the coefficients as actually mole ratios. So I can have 2 moles of butane will react with 13 moles of oxygen to form 8 moles of carbon dioxide and 10 moles of water. Since both the number of molecules and the number of moles are counting numbers, they both communicate a number of atoms or molecules. I can do this seamlessly between the two, and the coefficient would be the same. So here's kind of a how to balance chemical equations checklist. First, you're always going to write out the chemical equation and make sure you have the correct formulas. Without that, this kind of falls apart right away. Now, the subscripts of these chemical formulas can never be changed when we're balancing an equation. We're only going to change the coefficient in front of the chemical formula for each molecule. Next, we're going to balance the equation with coefficients, and we're going to balance this one element at a time. We're not going to tally all the numbers of atoms up at the beginning, and we're not going to do it every time we change a coefficient. It's going to be a lot of small pieces of mental math that leave a lot of opportunities for simple mistakes that, even though we're doing the problem right, can make us spiral down a track of lost time for a while. So after we go through and we balance each element, then we'll come back and make sure that the smallest set of whole numbers is used across our coefficients. So we can't really have half a molecule, right? And then we will make sure that everything balances out at one last double check. So I'm going to walk through an example, and then we'll have a practice video or practice problem with a video solution following that. So here I have a pretty big equation. I've got this C3H8S reacting with oxygen to form carbon dioxide, water, and sulfur dioxide. This is a type of combustion. So I'm always going to start, in this case where I don't have heavy elements, I would start with any metals first that were heavier. And so now what I'm going to do is kind of evaluate which are my easiest atoms to balance first. And I noticed that my carbon is in only one reactant and one product. And my hydrogen is in only one reactant and one product as well. Looking at my sulfur, it's in one reactant and one product. So those I'll be able to balance by just looking at one thing on each side of my arrow. Now my oxygen is in just one of my reactants, but it's in every single one of my products. And that's significantly more complicated than the other three elements. So I am going to make sure I balance my oxygen last because it's complicated. All right, so I'll just start with carbon. It doesn't actually matter where to start exactly in this case, other than not starting with oxygen. So I have 3 carbon on my reactant side, and I can tell that by the coefficient 3. I have 1 carbon on my product side, as evidenced by a lack of coefficient. So I'm going to put a 3, or sorry, not a lack of subscript. So I'll put a 3 coefficient in front of my carbon dioxide. And now I have 3 carbons on both sides of the arrow. Now I'm going to look at my hydrogen. I have 8 hydrogen atoms on my reactant side, and I have 2 hydrogen atoms on my product side. So if I multiply that 2 by 4, it'll equal 8. Now I have 8 hydrogen on my product side, and I have 8 hydrogen on my reactant side. Hydrogen's balanced. Now sulfur. I have 1 sulfur on my reactant side and 1 sulfur on my product side. Hey, it's done for me. I don't have to do anything for sulfur. So now that I have all the easy elements done, now I actually have to balance out my oxygen. And so looking at my oxygen, I have 2 oxygen on my product or reactant side. And for my product side, I'm always going to take the coefficient and multiply it by my subscript to determine the number that I have for any element. So I have 3 times 2, which equals 6 oxygen. Then for my water, I have 4 times 1, that equals 4 oxygen. And for my sulfur dioxide, I have 1 times 2 for 2 oxygen. And remember, for these, this column is representing my coefficients. And this column is representing my subscripts. All right, now I'm going to add all of these up because they're all in my products, even if they're in separate molecules. So it's going to be a total of 12 oxygen. So I have 12 on my product side and 2 on my reactant side. If I multiply my reactant side by 6, I'll have 12 oxygen atoms there, and then everything is balanced. So now I have everything balanced. I can look and make sure that these are the smallest whole numbers possible. Because I don't have a number in front of sulfur dioxide or the C3H8S, that means there's really 1 mole of each of those molecules in my reaction mixture. So I can't make this any smaller than the number 1. So I'm not going to be able to reduce this in any way. So this is my least whole, or my smallest sized whole number ratio for all of my reactants and products. At this point, I can always double check and make sure that I have the same number of molecules on both sides. So I can look at carbon, then hydrogen, then sulfur, and then oxygen. Got my reactants and my products. So I have 3 on my product side, and I have 3 on my reactant side and 3 on my product side. And that's just looking at the fact that it's subscript 1 times, or sorry, coefficient 1 times subscript 3. And over here, it's a coefficient 3 times the subscript of 1. For my hydrogen, I can see I have, 8. On my reactant side, it's a coefficient of 1 times the subscript of 8. On my product side, I have a coefficient of 4 times the subscript of 2 for 8. For sulfur, I have a coefficient of 1 times the subscript of 1 for 1. And it's the same on the product side. So I have 1 on both sides. Oxygen, I have a subscript of 2 times that coefficient of 6 for 12. And then I have this calculation that I already did for 12 oxygen atoms on my products. So I was able to balance this without having to go back and rebalance any of the ones I did earlier in the problem.